open hardware product. So of the kind of research that we presented in the past, in 2007 we were one of the first ones to talk about card hacking. In 2009 we talked about sniffing keystrokes over the power line and using laser beams for laptops, which I thought it was very cool to use laser beams in a talk. And in 2011 we talked about breaking chip and pin and intercepting the pin pretty much everywhere. And last year we did a talk about packaging packets on Ethernet devices, and I also did one of the keynotes here. Mr. Conte was so gracious to have me having the keynotes here, which it was very nice. So, and today, after lots of talks about breaking stuff, I'm going to present about something that, you know, for a change we created, which is this USB Armory device. So what is it? It's a very tiny, as you can see, USB device, completely open hardware and open software, which is designed for personal security applications. So basically what we did, we wanted to squeeze a computer into a USB device. And the reason for doing that is to enable all different kinds of applications. The first one that we thought of was enhanced mass storage. So we want a mass storage device where we can encrypt automatically on the device with the means that we prefer. So whether it's OpenSSL, whether it's PGP, or whatever means. And also we thought, wouldn't it be so cool if such a device could actually also do malware scanning on the device itself with ClamUp or whatever you like, or refuse to, you know, to accept certain files. And such a device, it could also be used to do data self-destruct. If you copy a certain files or if you don't do a certain action, then the device wipes itself automatically. And with this very basic idea enabled by having, you know, an embedded computer or USB device, then all other possibilities came up. As soon as we started the concept, we had all kinds of ideas. So I like to use it as an OpenSSH client. So if I'm on a kiosk, I just connect to this device with a one-time password or whatever password, and then I SSH out from it because my keys are stored on it. It can be used for Tor or VPN tunneling. There was very recently a failed Kickstarter about putting Tor on a router. Of course, with this device, you can just do it on its own. Because you can emulate network cards for USB. So this is what enables this kind of connectivity. It could be a password manager with integrated web server. So you have a nice web app where all your passwords are encrypted there and you unlock the password that you want. It could be electronic wallet. It could be authentication tokens for multiple protocols. And of course, having an embedded computer on a USB device could also mean that you can use it as a portable penetration testing platform. You can have Metasploit, you can have Kali, you can have all kinds of tools on the device itself, and you can decide to use them from the device or to automate whatever kind of attacks. And since in this specific case, by having an embedded computer tied to USB on the go, such as this device, you can also do low-level USB testing. So the same thing that Travis Goodspeed's phase tensor does, but with a little more power, a little more flexibility, since you can emulate devices from using the Linux kernel USB gadget framework. So we thought it would be great to have such a device because all of these applications and even more then, you know, becomes achievable. So just to give you a little bit of concept, so enhanced mass storage, so what we do, we can emulate a normal mass storage gadget, and then we copy a file on it, we have ClamUp scanning it, GNU-PG scanning it, or whatever, and then it gets stored on a micro SD card. We can take this concept further, and we TCP IP over CDC Ethernet. We do the same thing, but then we can also do communication from the device, either for uploading the file somewhere to Dropbox, Google Drive, whatever, to email it out, or to do it completely client-side. So the device will give you a link, and then your browser, using the cookies that are stored in your browser, can upload the file. All things that, of course, with normal USB drives now are inconceivable because they're either locked in functionality or they're very single purpose. And again, data self-destruct, you can decide if I copy a certain file on it, or even if I refuse to do a certain action, or if I copy a file with a certain name, then everything wipes on itself, or activism and people that do tend to care about these kind of situations. SSH proxy, pretty straightforward. So if you're an internet kiosk, instead of typing a password for your SSH connection, you connect to the device and then you SSH out of it. Password manager, pretty straightforward. You can have a web app on it which unlocks specific passwords. You can search a password for a certain website and unlocks it. And authentication token, very easy. You can have the Google Authenticator on it. You can have, we're working to get Ubico, UTF on it, and so on. But there's one feature which I really like, which I think is probably one of the coolest features which I haven't seen so far in any device like this, is what you can do by having such a device is that you can have the device itself authenticating the host. So by whatever means, let's think of something very simple. You have an SSH server on your laptop, and as soon as you plug the device in, the device fingerprints your SSH server. And if your SSH server doesn't have the certificate which has been previously provisioned on the device, then it will refuse to communicate to you. Or it will decide to show you a completely different set of files. Or it will decide to wipe itself because you want your device only to plug on your laptop, and if it's not yours, it will decide to wipe itself. So all of these applications can only be possible, I think, with such a device, because you need an open source device with a software which can be customizable to do these kind of things. And normal USB devices, of course, nothing exists in this form factor that would allow you to unlock these kind of possibilities. So for these reasons, we thought it would be a great idea to have such a device. And we searched around and there was nothing of a sort. So as a challenge, we said, let's make one, let's build one. And we test hardware and we build hardware for security testing all the time. But of course, this was something which was on a completely different scale in complexity and final goals. So we thought we like a good challenge and let's do it. And by enabling all these kind of applications, we set a very few design goals. So of course, it has to be a USB powered device, where it doesn't mean that the power comes from a USB form factor plug, but it means that the amount of current that the standard USB port gives should be enough for powering up this device. So it has to be powered with less than 500 milliamps. It needs to be a little bit future-proof. So with lots of devices and lots of microcontrollers, you're limited by the power. You can only use firmware with a very low footprint, and this really requires a lot of optimization and customization for the code that you need to execute on such a device. We didn't want that. We think that if you want to create an open platform which is successful, we need a fast CPU and a generous amount of RAM. It needs to have secure boot. Okay, so this is very important also with the recent, bad USB kind of thing. You want the code that runs on of this device to be signed if you want to, and to only run on the specific device that you hold in your hand. It needs to provide standard connectivity over USB. So of course you can add mass storage, but we wanted to be able to emulate all kind of USB connectivity options. Really important. It needs to have a familiar developing and execution environment. So there are a lot of chips and cores that you can use from different manufacturers that they support Linux somehow, but they require a lot of patches from the actual vendor in order to run. So there are a lot of Maxim chips, for instance, which they do run Linux, but you need to use the specific kernel version which is done by Maxim. Is most of the time is a very old kernel, like something in the 2.x series, and it is something that we wanted to avoid. We want to use stock OSs and stock kernels on such a device, because otherwise it will limit developers' capability a lot. So this was one of the design goals. And then of course it needs to be open design, and with open design I mean that not only the software, but also the hardware needs to be open. With the NSA leaks, of course, now we talk a lot about supply chain attacks and trusting your hardware. So find ways where you can actually audit and measure the fact that your hardware is not being tampered with. So by having an open hardware design, we minimize this concern. Not eliminate, of course, we minimize these concerns as much as we can. So we thought this needs to be a completely open design. The first important task into this adventure, of course, is selecting the CPU and the system on a chip that we want to use. This is a non-trivial effort into making the right choice and making it so that it doesn't bite you at the end when the development process is kind of halfway through. At some point, it's not really good to go back and change, making different choices. So this was a very critical decision from the beginning. And the choice for the USB Armory was to use the Freescale IMX53 system on a chip. So this chip has various reasons why it was chosen. So first of all, it's powerful. It's a Cortex-A8 ARM CPU that can go from 800 megahertz to 1.2 gigahertz of clock. So it is really fast. And you can decide whether to clock it, at a lower setting or a higher setting. And one of the nice things about this family of devices is that almost every datasheet and manual is public. There's no NDA required, and for instance, the secure boot functionality is described into the public datasheets. Now, I wouldn't go as far as saying that the Freescale documentation is great, because when it comes to hardware, having great documentation, it's an illusion, it's a utopia, but I have to say that they're far better than any other vendors. So that was certainly going into their advantages. And when you're developing such hardware, you're going to read a lot of data sheets, like hundreds of them, and they will have 500 pages, and you got to understand all the little hidden, things that are in there that can bite you later on because, oh, I didn't notice that errata, and this thing is not going to work. It features ARM Trust Zone, which I'm going to discuss in detail in a few minutes. Secure boot, which is really important. It's one of the few system on chips which has a very respectable secure boot support. And most importantly, the secure boot on this device happens with keys that you, of course, provision whenever you like. So it doesn't work with predefined keys that are there already or something like that. It has secure storage internally and secure RAM for cryptographic purposes. There is a detailed power consumption guide available, which is very important. One of the very first concerns here, at the very beginning, we weren't even sure that such a device could theoretically exist, because we thought maybe at the end of the day the power consumption would be too much on a USB 2.0 port. So having hardware which gives you detailed power consumption guides, it really helps you a lot into assessing which one to choose. And to go back to one of the design goals, it has excellent native support. So it runs Android, Debian, Ubuntu, stock Linux kernel, as well as Android, with no change whatsoever, just configuration settings. And also, it is also supported by FreeBSD, and we're going to also start working making it supported by OpenBSD. And there's a few real-time devices that also support it, but I don't care too much about that. But it is fair to say that the support for this processor is very wide. So requires much less customization on our side and on the developers and user side to get code running on it. There's a good stock and production support guarantee, which of course is also very critical. You don't want to end up in selecting a part which you love, and then you realize that in 3 months it will be out of stock and you have to change your whole design. That's something which is really important, both with the big components like the CPU, as well as other components like the RAM and the crystals and so on. Good stock is a prerequisite on pretty much all of the parts that you're going to use when you're making hardware. So the system on a chip supports a whole lot of interfaces. He has CAN bus, he has lots of controllers, he has multiple USB host and device ports, serial ports, I2C, SPI. It has a very powerful VPU and GPU, which of course we're not using in our case because we don't have any display, but it has a lot of impressive features, and it supports different kind of memory modules like DDR2, DDR3, so this really gave us a lot of flexibility in deciding what and how to connect to it. And it has native USB on-the-go support, which is important for our applications, so it can natively support acting as a USB device. So, ARM Trustum. So what is ARM Trustum and why it is something that it was interesting for this application and why we want to use it. So Trustum, it's a feature which is present into certain ARM cores which allow you to completely have a layer of separation between what is called the normal world and what is known as the secure world. So basically what you can do, you can switch the state of your CPU to either a secure or a non-secure state. And whatever memory you allocate in one of these two areas, it remains contained into that area. But it's not only limited to that. This security state also propagates on the hardware, so on the other controllers which are connected to the board. So if we have an interrupt controller here, if the Trustum support is correctly implemented, then the interrupt controller will be aware of the Trustum security state. The memory controller will be aware of the Trustum security state, and so on. And this allows you to do things such as allocating a certain hardware resource only to one of the two words, or both of them, you can decide. So, for instance, you can say the USB controller, or the serial controller, or the SD card controller, only the secure word can access them. And if the normal word try to access hardware which is not allowed to access, then an exception is raised and the secure word has a chance to decide what to do. So what you can do with this technology, you can decide to place certain codes into Trustum, and then you can have an API between the normal word and the secure word to have the two containers communicate with them with a very precise API that you define. And if you want, you can decide to confine certain hardware only to the secure word. So for instance, what you can do, you can have the secure word handling the SD card controller, and you can have the secure word exposing a virtual SD controller to the normal word, and the secure word handles all the encryption and stores the security keys. Now, suppose that we have Linux running on the normal word. If your Linux instance gets compromised, even if you're root on the Linux instance, so you have the maximum amount of privilege, you cannot access or check the memory of the secure area, and you cannot communicate with the hardware that the secure area is protecting. And this is enforced by the system on a chip architecture. The interesting thing is that in this way the device kind of becomes like a soft smart card, in the sense that you can have HSM functionality without relying on a flashed read-only firmware on the device. So you can decide at boot time what to put into that compartment. And if you have secure boot, of course you can do it in a way which is secure, because you control the whole signature chain. Now there's already one operating system which is called Gnode. There's a link there. It's a Gnode OS framework, which already supports natively Trustum for this specific system on a chip. Now they're supporting on a tablet, so they do something a little different. So what they do, they virtualize the touch screen and all the input devices which are within the secure word domain, and they virtualize that to the normal word where Linux is being executed. And keep in mind, the interesting thing here is that we don't have a hypervisor. So the two separate environments, they just run at the same time, or they are present into the memory at the same time. And when you switch the context between one of the two containers, the other one can continue to do its job. So it is much easier than just virtualizing your environment for your Linux system. The Linux system, let's say that here it's in the normal world, can access pretty much every hardware that it wants to natively. The only thing that is virtualized is the hardware that we want to keep under control of the secure world. And we plan to use Trustzone to contain cryptographic applications even further for people that want another layer of separation. So of course, the concept of such a device is that you have an external device, so that maybe you don't trust too much your laptop and you want to offload functionality on the external USB device. But with Trustzone, you can have even a further layer of separation. So even if you decide to not trust the Linux OS which runs on the USB device, then you can place critical functionality within the secure Word container. And leveraging on Trustzone is one of the first things that we're going to do after the final hardware gets delivered. Now, one of the other reasons why the IMX53 was chosen is that it has excellent Trustzone support. So what does this mean? So Trustzone, it is something that within the ARM core, it is done by ARM. So there are very little variables there. But Trustzone doesn't tell you exactly how all of the hardware which is around the core should interact. So you can have certain chips from manufacturers which they don't provide a very good Trustzone support, meaning that the external hardware components in the system on a chip are either not aware of Trustzone, so you cannot decide to confine them to one of the two security containers, or they don't provide you a granularity in detecting where the access is coming from, which is good enough for your security reasons. What they might do, they might have a bunch of I/O interfaces, and they all come with the same security ID. So in certain chips you have Ethernet, USB, serial, they all belong to the same security context from a Trustzone perspective. So you cannot split between them very, very effectively. And we evaluated that in the IMX53, this separation is done in a way which is fine for our needs. So what was the development timeline? So in January, we had the first concept idea, which was based on a completely different Atmel chip. Then we changed our mind, we narrowed down exactly what we wanted to do. And in March, we began to develop the schematics. In April, so a month after, we had the PCB layout for a breakout board, which I'm going to discuss what it was. And in August, we placed the order for the first alpha board. The alpha board arrived 3 weeks after that. The alpha board worked the very first time, so we're very happy about that. That I think saved us 6 months of development. And so in October, we went live and announced the project. What we did very recently, we did 7 optimized revisions to narrow down the price of the device. These 7 revisions arrived, I think, 10 days ago. We evaluated them. We just finished evaluating them, actually. And yesterday, we placed the order for the release candidate, which is going to arrive. Hopefully, all the fixes will be there. It will work just fine. And that's where we make the first production batch. And of course, we've never done anything like this. We were not familiar with all the process that goes into going from idea to actually almost mass producing hardware. So it was a very fascinating journey. And I'm going to explain to you certain lessons which were learned from all of this journey. So these are the specs of the final design. It's very tiny, 65 by 19 millimeters. It can be USB horsepower. It consumes about 200 milliamps when you use the CPU at 40%. We have a micro SD card slot, so there's no persistent storage on it other than a few configuration settings that you can put on the system on a chip. So the code gets all booted from the micro SD card. We put a 5-pin breakout headers with GPIOs and serial and UART console, which can also be reconfigured for I2C and SPI if you want to. we have one LED on it, which we're going to use with Truston, and this is why. With Truston, you can also decide to assign certain GPIOs to one of the two containers. So by having an LED on the device, what we can do, we can make it so that when the LED is turned on, you know by design that the secure container is being executed. Because the normal container doesn't have the hardware privileges to turn that LED on. So we put one LED on to give you the feedback of when secure mode is being executed. So that if at some point you have code which is supposed to be in the secure container and which asks you for a password, you look at the LED, and if the LED is on, you know that the normal container is not trying to spoof that functionality. Native support, as we said, and we test the emulation of all kind of devices, HID, Mac-Store, CDC, Ethernet, and it works just fine. And it's all open. And actually, the design for the alpha board have already been published on GitHub, and they're there with under GPL license. So, lessons learned during the development. What are the main challenges into doing one of these little hardware? So first of all, you're dealing with BGA footprints. So BGA stands for Ball Grid Array. So that there is the actual system on a chip, and there's also the DDR module, which has the same footprint. So what happens there is that under the system on a chip, you have 554 little balls that are what actually will be soldered on the PCB. And the challenge there is that it is fairly complicated, if not impossible, for you to reliably solder and desolder these components by hand. So the whole prototyping, which we were used to do with breadboards, and with easy components that we could wire up together, when you have such a device, it becomes almost impossible to do in your lab. Which means that when you actually want to try it out, it becomes complicated. So we thought, let's try to be smart, and let's create a breakout board. So this is the way you fan out, that's a term, all of the different connectors on such a component. So what you do, you have your copper pad, which receives the little sphere under the BGA, and then you create a via. So a via is a connection that goes through all the layers of the PCB, and you break that out with a trace. So what you see in this image, the red circles are the actual pads where the system on a chip lands, and the gray circles with a hole in the middle are the actual vias where the traces come out. And all of these chips are designed so the middle section is power and ground, so that you don't have to break it all out, because otherwise it would take you 20 layers to break everything out. And all of the external balls are the ones where you actually have all the signals. So we can see that we break out on the left, we break out on the right, and we break out on the top and the bottom. And this is the design for a breakout board. So this is the breakout board that we designed. We designed similar breakout boards in the past for doing reverse engineering, but this time we wanted to have a breakout board for this specific footprint, so that we could actually easily test the system on a chip capabilities. And we didn't want to solder or desolder anything because we thought that's going to be an expensive mistake to make. Because when you make boards such as this one, if you only make 2 of them, they're going to cost 400 euro each board. So we bought a socket. There's a company which only makes these sockets. They're very pricey, but the socket that you see there on the right allows you to clamp the system on a chip without having to solder anything. So you have a precision torque screwdriver, you have the exact amount of pressure, and this socket receives the system on a chip without any soldering, and it makes a perfect connection, which also works for high frequencies. And the socket itself is also clamped on the board itself, so we don't even need to solder that. And we thought, with this board, we can break out everything, and we power it up, and we can test everything except the RAM, because I'll tell you later what's peculiar about the memory. So this was a failure. You see there Darth Vader saying to the Admiral, "You failed me for the last time." So, and in reality, I'm Darth Vader and my colleague Andre is the poor Admiral, because he made about 10 of these boards. And what are those? Those are the components for powering up the system on a chip. So powering up such a system on a chip, it's not as easy as just wiring, you know, plus and negative 5 volts. You have about 7 different rails of switching power that you need to provide. And there are components, such as the one which is there in the middle, which are only designed to provide all the different voltages to such a system on a chip. The problem is that the tolerances for the distances of all the various inductors and capacitance and the quality of the connection of the traces, the tolerances are so high that by doing by hand all the soldering, you will never get it right. You will always get at least a couple of rays that will not work. So at the end, we learned the hard way that this approach actually doesn't pay off. And what you should really do is just go for the final form factor for the power supply that you want at the end. And since you need a PCB for doing that anyway, and since you cannot test memory anyway, the bottom line is at the end of the day, you have to do your first alpha design right from the beginning. Everything trying to be smart in the middle to save money into making PCBs doesn't really pay off. So this breakout board turned out to be like a superstar destroyer. It's something which is big, clunky, expensive, and at the end of the day, it just doesn't work and it gets beaten down. So Darth Vader was not amused. One of the other challenges into doing this kind of thing is that, so we wanted it to be completely open source, open hardware and open software, but open hardware doesn't only mean that you publish the schematics, you also have to publish the PCB layout, and ideally, you also have to publish the project file so that people could actually read it and modify it. Now, there are lots of very wonderful commercial tools for PCB development, which are really, really expensive. Certain licenses start from 7,000 euros, which to really make it easy and great to, you know, develop such a board. In our case, we wanted to use KiCad, or KiCad, whatever you want to say, which is an open source tool for PCB development. Now, the problem with using open source tool for this kind of task is that it takes about 7 times longer the time that it would take with a professional PCB layout tool. This is not necessarily true for all design, but it is true for designs where you have such high specification and that you need to route memory with a lot of constraints. So the problem with memory is that when you use DDR2 or DDR3, you have about 60 or 70 different traces that they need to go from your system on a chip to the RAM, and they all need to be exactly of the same length, to the, you know, second decimal of a millimeter. Now, KiCad doesn't make your job easier into doing this because it doesn't allow you to swap traces very easily. It doesn't allow you to ask for a trace of exactly a certain length. It becomes complicated. And in our specific case, things were also complicated by the fact that we have our RAM module on the right side, and the only way we can route to it is by using one axis. So normally, if you have a bigger board, you can go around the memory, so you can go multiple ways, and you can do all kind of loops in your traces so that the length matches. So it is still a pain to do it, but it becomes easier if you have more space. In our case, we didn't have a lot of space, and also on the bottom of the board, we also want to put the micro SD card slot, which takes some space, and it takes space that then is devoted to the bias. So this was, in my opinion, the most complicated task. And you know, at the end of the day, I think it's great that we managed to do it with an open source tool. So I don't want to criticize KiCad for this, but you know, just so you know, it takes quite longer than using commercial tools. Now, of course, as it goes with open source tool versus commercial tools, capabilities which are actually not that useful, like the 3D graphics, they're much better in KiCad opposed to commercial tools. So it was nice to be able to visualize the board and see what it looks like. You know, there's some aesthetic to it, which of course in electronics engineering they will tell you that aesthetics is the least of your concerns and you should not worry about it. But you know, we're Italians, I guess. We like fashion, whatever. So we wanted the board to also look nice. So we went as far as aligning certain components because we thought it was nicer. And we didn't mess it up by doing that. So this is the first Alpha board that arrived. And part of the reason why I'm doing these talks is also to inspire people to make hardware. Because at the end of the day, it is difficult, but if we can make something like this in 2 to 3 months of time, I think, you know, everybody can. And making hardware, it is scary, but it shouldn't be as scary as you think. So you can see in the development process that we did the whole breakout board because we became a little paranoid about not failing and making our life easier. But this is the thing, the Alpha board worked at the very first attempt, which is something that to us was almost inconceivable. So this, you know, is a testament to the fact that with effort and, you know, even with open source tool, you can build something which it has really high specification and it's really, you know, in theory, it's a really complicated device. So the Alpha board, you can see it's a little larger than the final form factor because it has JTAG connection broken out so that we could easily test in case there was a problem with the memory module or with the SD card. With the JTAG port, we can easily debug what's going on. Of course, that doesn't help if the power doesn't work. That was our biggest concern, to power up the SoC in the first place. Because if it doesn't power up, then you also don't have JTAG, and it becomes very difficult to exactly probe what was going on. But luckily, this wasn't the case. And there's also one very important thing to understand here. The fact that you can put components in your design tools and that you're respecting all the tolerances and that you click on the DRC, the rule checking, and it will tell you that everything is great, doesn't really mean that you can reliably manufacture a board. So what we learned is that it is very helpful to find manufacturers that will really guide you into the process of understanding exactly where the soldering of the components is likely going to fail. So in our experience, some manufacturers, they just don't care. They receive the Gerber files, which are the design files that you need for the manufacturing output that you need for making the board, and they would just try and make it. And if it fails, then it's going to be your fault. But some other manufacturers, they really engage you in letting you know that certain things can be improved and that by spacing certain components a little more apart than what their respective data sheets says really helps into reliably making the components at the end. And also one very stupid thing, when we made the Alpha board, we only made 2 of them. Never make 2. 2 is a silly number, right? Because manufacturing can go wrong on a certain percentage, and if you make 2 boards, it can go wrong for both of them. So make 20, you know, and maybe 2 or 3 will not work, but the other one will work. So that was also a mistake. But in our case, we got really lucky. Both boards, they worked right away. So here we have another picture of Darth Vader being happy because the JTAG connection was working right away. Serial connection, here you see a bus pirate connecting over the serial port. So the serial port was very useful to develop the technique for flashing the SD card, because of course we put the SD card in and it boots up, but if you don't have a serial console, it becomes difficult, of course, to understand what's going on. And in certain components, certain processors, you can have a serial console from the bootloader over USB. So for instance, I think on the OMAP chips from Texas Instruments, U-Boot natively supports giving you a serial console over USB. In this case, there was no such functionality. We might patch that in later on, but for now, we just use the serial port, which was broken out. And here we are testing the GPIOs and the power consumption to make sure that all the power consumption was correct, and that if you would power things up with GPIOs, then there wouldn't be any surprises there. I like this picture because it's funny because, you know, again, nowadays with open source tools, 3 months of work, you can pack an entire self-sustained computer which has pretty much the same power of a Pentium 2 processor, which was way bigger than that, and that was the only processor. So I think it's pretty amazing that nowadays, just with open source tools, we can do something like this. And who knows what we'll be able to do in 2-3 years more. So these are the beta boards that arrived. So we made 7 different revisions trying to reduce power consumption, reduce the cost of the components. And this is almost identical to the final design. Of course, it has to be black because black is cooler than green boards. So I think that was very important. So it comes in black. And as you can see, we, of course, the final factor doesn't allow you to have a big JTAG connector, but we decided to do little test pads here where we're actually breaking out the JTAG connection if by any reason someone needs the JTAG connection. So they're not really easy to solder on. We might even make a debugging board which just has the debugging needles necessary to access those. But yeah, we thought it's still better to have them. So we learned a few lessons. There were some inductors which work just fine, but after 2 weeks they come off because they're too fragile. And it is very important to figure it out before you make 1,000 of these. So it was really nice that we realized that, and they come off not because of the quality of the soldering, but because the component itself is very fragile to external stress. So now we replace all of those with a footprint which lead to no issues whatsoever. So that's a very important lesson. You need to make sure that the components that you put on them, not only they work from an electrical standpoint, but they will also sustain the stress that either with a case or without a case, the board is gonna receive. And this was another interesting one. So the USB connector needs to be gold plated, because if it's not gold plated, after 40 times of insertion, you will lose the connection. So what you do, you ask the manufacturer to do the gold plating for you. And what they have to do, they have to put somewhere on some pad or some connection where they can use to deposit the gold. Now in the beta boards, we experienced this. If we would plug them in, the boot process is delayed by 5 seconds. And we're like, what's going on there? And we look at the design, we try to understand what was changed from the alpha board, which had no such problem. And you know, we couldn't find anything in the changes of the components that would account for this. And then we're like, okay, 5 seconds, that's a very precise amount of time. So let's look into all of the data sheets of the power components where we can find 5 seconds. And we find that the voltage regulator has a 5 seconds wait time in case it detects a fault. And in this specific case, an under voltage fault. And we also realized something else. If we would plug the device into a USB cable, and if we would then plug the cable to the laptop, the problem would not be there. So we're like, what's going on here? And this is what happened. So these 4 traces that go from the pads to the outside, which we didn't make because they were made by the manufacturer for doing the gold deposit. Here the PCB was cut, and we have very tiny 4 little dots here, which are actually conductive. So when the PCB is inserted into the USB slot, the 4 connectors inside the slot, they first make contact on those 4 points, then they lose contact because you have some space between those and the pad, and then they attach to the pad. So you have an intermittent power supply, which creates the under voltage fault condition. And you don't get this when you use an extension because the USB connector doesn't have this issue. So now we're going to do the plating in a completely different manner, which is going to be immune from this problem. But you know, something really silly in the end, which took 3 days of bashing our heads on the wall to understand what was going on. So this is a very good lesson learned. So we hope that in 3 weeks we should have the final release candidate, and that's what is going to be in mass production. So before getting questions, I just want to show you a demo. So now I have a device here. You can see layer if you want. I'm connected to it. So you can see it's just a normal Linux system with ½ gig of RAM, our processor. I can connect to the internet from it. Oh, maybe yes, I can, maybe not, because I'm not routing it yet, sorry. Oh yeah, I am. So I can connect to the internet, do apt get update, like I would do on a normal system. And you know, just one of the very first things that I did on it, I put a Bitcoin wallet on it, just because I can just use it. And this is from Windows, by the way, so I'm exporting X, and this is a Bitcoin wallet. So I'm using my system as an I/O, just as a keyboard and as a screen for a Bitcoin wallet, which can be unlocked and it runs on my USB device. And this is just one of the 20 applications that we can think of. And the price of this device will actually be closer, if not less, than Bitcoin wallet solution that you can, hardware Bitcoin wallet solution that you can find, which are not open source, or at least maybe only the software is open source. So in my opinion, having such a powerful USB connected device, you know, you can instantly see the application. And this was done 2 hours after we got our first alpha board. In 2 hours, we were able to run Linux on it, SSH to it, forward X, and then launch a Bitcoin wallet. And in the next months, we will actually create the first Polish application for it, which will be the one concerning the advanced secure file storage. And if you have any ideas of applications that you would like to see on the device, of course, I would be happy to take them and to consider, you know, taking the lead into the development effort, even if the hope at the end is that we will create a community of applications for it. So, thank you very much for your time, and do we have time for a couple of questions, maybe? Thank you. One question over there? In the meantime, I'll shut it down. Let me do shut down on my USB device. There you go.
So I was wondering where the keys for TrustZone are stored. Are they stored? Are they stored on the SD card, or are they stored on some persistent storage elsewhere?
Right. So we could have placed persistent storage on the device, but we didn't want to, because then you would have been able to you know, plug your probes there and extract the keys. So we intentionally didn't put any persistent storage on the device other than the SD card and other than the public keys which are used for secure boot. So for secure boot, you fuse 4 keys into the sock, and once you have fused them, you cannot change them. And those anyway are public keys that are used for the boot process. You can revoke 3 of them. If you revoke the last one, the device will not boot with anything. The way we want to use TrustZone, so TrustZone is all software, okay? We want to do it so that you unlock or you input a passphrase at boot time, and that will decrypt the contents of the SD card, and it will place key material into TrustZone right away. But so the key material will be encrypted on the SD card, and the way you unlock it is by you placing the passphrase in the first place. Also because we want to avoid that if I steal your key and I plug it into my computer, it gets unlocked with all the key material and so on, even if it goes in TrustZone. So at some point we will have you to input and to unlock it. Just as the way you do with smart card. You always have a pin at some point that unlocks the device. This will be identical, but instead of a pin we can decide whatever we want to. But that's why we don't have persistent flash storage on it, because it's really difficult to have secure flash storage, especially into such a compact device. Does that answer your question?
So I think specifically, I just wanted to know how you were validating that the SD card was your SD card.
With secure boot.
Okay.
So with secure boot, the bootloader is loaded from the SD card, and secure boot verifies that the bootloader is signed. Okay. So if you provision the device with your public keys and you have anything else other than your signed bootloader, it will not boot. And then it's the bootloader responsibility to check the chain of trust for everything else. And the complex way is to put Linux, and then Linux verifies the binary and so on. We think an easier way is to put a blob into Trustzone, which is signed, and then Linux is untrusted, and you do you delegate the secure part to Trustzone. But anything can be achieved. It is absolutely no different than using secure boot on your laptop with UEFI. The difference is that here you control the keys. They're not from the OEM. You can decide what they are. Any other questions? Yes?
Are already PCB schematics, layouts, and code published somewhere?
Yes. So there's if you go into the project page, which is you go to inverspath.com or you go to github.com/inverspath, there are separate repositories for the bootloader code, and there's all the KiCad project files. So with KiCad you have the electrical schematics as well as the PCB layout. Now you only have it for the alpha board. As soon as we decided what the first version layer will be, we will also publish those.
And could you estimate a cost? If for example, I want to buy some today.
We're narrowing down the cost right now, but I think it will be no more than €100 per device.
Okay, thank you.
Any other questions there?
Great presentation. I have not only understood simple things.
Okay.
When you have spoken about the secure boot key.
Yes.
You have stated that they are memory stored where?
So on the system on a chip, there are some. They call it fuses. So there's a memory for configuration, which certain areas you can only write them one time. So there's a procedure which involves writing certain registers where you fuse key material on the system on a chip. In this case, you fuse the hash of the public key that is then used for secure boot. So he has persistent storage. I think he has 128 kilobyte of configuration value, so not too much. And some of it's one time, right? Okay. And it's on the system on a chip itself.
Okay, but this means that you can only use, you can only change the operation system inside the platform only 4 times, no?
This means that if you plan to use secure boot, you can put 4 keys and you can put them one time only. Okay. If for some reason you lose the private keys for those, you gotta buy a new one. And I mean, this is good for security, right? You don't want to be able to change them. So, but you have 4 keys, right? So you can make it sure that you can revoke 3 of them if you want to. But yeah, that would be a problem in our development. If we mess it up, we lose one of them. So yeah. Gotcha, thanks. Yeah.
Okay, one question. What would be the cost, price-wise, design-wise, and component-wise, to add a USB connector to connect some kind of, any kind of HID input device so that you could input the key material securely?
So well, that you can also do it not over USB. You have other pins that you can use. Maybe you can attach, so we have GPIOs on it, so you can attach a keyboard over the GPIOs. But anyway, it can be done, it can be easily done. It's only a matter, it's not a matter of changing the design, it's only a matter that whatever change that you want on it, you need to make at least 100 devices so it's cost effective, possibly even more. So the price breaks right now, we have to make 1,000 PCBs in order to be cost effective, and we can assemble them in batches of 100. Okay, so if we make 1,000 PCBs, each PCB is going to cost about €5. So that's 5,000 euros, and then we can assemble 100 of them in turns. So if you make a change, you got to account for that. But depending on the application and the customer, whatever, that might not be a huge cost, of course. That's the only challenge. So it's very easy to break out USB hosts. He has 2 USB hosts. So one of the other things that was suggested is that if we break out the USB host, then it can act as a USB filter. But that means that you need to plug it with a double cable because you need double the power. Because if you're a USB host as well, you cannot use the USB power and so on. But yeah, it can all be customized. We can even put 2 Ethernet ports, make it a little bigger, and do a Tor router completely open source right away. I mean, there's a lot of applications.
The network routing you showed, is that something custom, or are you acting like a network adapter?
We're emulating a CDC Ethernet driver, which is present by default on Linux, Windows, and Mac OS X. So by default, if you plug it in on Mac and Windows, it will detect it as a network card. It will nicely run a DHCP client. So if you have a DHCP server on it, it will hand the same IP address all the time, and then you have your address. Now, routing it on Linux, it's 2 commands by root, or in Ubuntu you can select to share the connection. On Windows, you just share the connection, and then it can also be routed. On Mac, I don't know, I've never done it, but I just know that I can connect to it. So we're lucky that because of Android phones and so on, the CDC Ethernet driver now is everywhere, and it's present there. So we just emulate that, and it's actually easier to use that kind of connection than any other connection.
That's cool.
Thanks.
Any other question?
Okay, thank you very much.